I am recording this. I'll let you know what's important and what you should copy down. Right now we're just going to begin with what is an exponential function. An exponential function is a function that has an exponent that's a variable. So this is an exponential function, y equals 2 to the x. Like lines, when we used to graph lines, y equals mx plus b, we'd have something like y equals 2 times x plus 1. But the x was a regular x. The x was not an exponent. So what makes a function an exponential function? That you have a variable that's an exponent. That's what makes it an exponential function. Okay. So what does the exponential growth function y equals 2 to the x look like? Now you might be thinking, why the heck did he put parentheses right here if this one didn't have parentheses? I'm going to put parentheses, and I'm going to be putting parentheses around the base from here on out because I will be introducing other numbers, other values. So for example, I might in the future put a 3 out here in the front, so it'll be 3 times 2 to the power of x. And if I didn't have parentheses, then it would look like a 3 and a 2 would look like a 32 to the x power. So that's why we're going to start using parentheses around that base. Anyway, what does the exponential growth function y equals 2 to the x look like? Well, here it is on Desmos. And you simply type in y equals parentheses 2 and then the power button and put the x right there, and you will see this graph on Desmos. So hopefully everybody had the time right now to go to Desmos, type in y equals parentheses 2 close parentheses to the power of x, and you should see this graph right here. Okay, so we know that an exponential function looks like this when it has the variable in the exponent. But how do we know it's an exponential function when it comes to the actual graph itself? An exponential growth function from left to right. We always look at graphs from left to right, David. So from left to right, it really does grow away from the asymptote. I hope we remember that the asymptote is that invisible line that your graph never actually touches, just infinitely approaches. So it's a growth function because from left to right, it grows away from the asymptote, in this case the asymptote y equals 0. And I actually typed that up right here. It says from left to right it grows away from the asymptote, but from right to left it infinitely approaches the asymptote but never actually touches. So we always look at graphs from left to right. From left to right it's growing away from the asymptote. In this case the asymptote is the x-axis, which is the line y equals 0 in this case. Okay. And from left to right, it's growing away from it. Like, look, right here, there's not much distance between. But as you go this way, there's a bigger distance. You go over here, there's a bigger distance, right? So as you go from left to right, it grows away from the asymptote. Now, that's why it's called a growth function. Tomorrow, we're going to talk about decay functions. And decay functions from left to right start way up here, and they decay down towards the asymptote. So decay functions tomorrow, we're going to see a curve this way. But today, growth functions from left to right grow. But if you're looking at it backwards, it decays or it shrinks towards the asymptote infinitely. But looking at it the way you should, from left to right, it grows away from the asymptote. I hope we understand the visual explanation of what an exponential growth function looks like. From left to right, it grows. Let's move on. So the exponential growth function, y equals 2 in parentheses to the x power, it will transform. What does transform mean? It's going to change if I add other values to it. Example, instead of just y equals 2 to the x, what if I put a 3 out here in the front? What if I put like a -4 or a -0 or a +2 or a -4 out here at the end? All these different values that I add on will change the way that first graph looked like. Okay? So let's begin. Let's see how each of these values changes the original y equals 2 to the x. So what I would like you to do right now is graph y equals 2 to the x on Desmos, which you already did. You probably still have it on your screen. And I want you to compare it to y equals 3. Put a 3 in front of it and see how it changes. And the question is, how did the 3 transform the graph? How did it change from this original graph to this new one with the 3? I'll give you guys a couple of seconds. I'm going to pause it, and we'll continue in a bit. So Destiny, I just asked you what changed. As you said, it got taller. And yeah, okay, so check this out. Here's the original, the one you saw. And if you put a 3 right there in the front, this is what you're going to see. So it did change, and you know what? Instead of seeing it separately, what we could do is go back to the original and hit enter, so you could be on the next spot, and you could put the next one with the 3 right in front below. That way both of them will be on the same graph. So as you can see, I just typed those in. I put the original, y equals 2 in parentheses to the x power. Then I put y equals 3 out in the front, parentheses 2, close parentheses, to the x power. And on my graph, it says that the original is in red and this new one's in blue. And we could look at that right here. And what do you visually see from the original red to the blue? Just like you said, Destiny, it looks like it got taller, right? In mathematics, especially in Algebra 2, the transformation with the correct vocabulary words from here to here is called a vertical stretch. Okay, a vertical stretch. So that value of 3 that we put out in the front, that's actually called the A value. We're going to get to that in a little bit. But that 3 that we put in the front is the A value, and that caused the original parent graph to stretch from this value of 1 stretches to a 3. And that makes total sense, because if you look at the value, the number out here in the front, what number is invisible out here in the front? That's an invisible 1 out there in the front, right? And this new value of 3, so this makes sense that on this parent graph with the A value of 1, it crosses the y-axis at 1. With this 3 out here, it now crosses the y-axis at 3. And this number out here in the front is called this number out here in the front is called the A value, and it's giving us a vertical stretch. Again, from the original red that was right here, it got stretched by 3. It got stretched by 3. What if I would have changed that 3 to a 4? What would have happened? It would have gotten stretched to 4. What if I would have changed it to a 6? Then it would have gotten stretched all the way to 6. Does that make sense? So that number out in the front causes a vertical stretch, or technically a vertical compression. We'll get to that in a little bit. But right now, I actually want to show you me typing in all of these different. Here's the original that we started with, and then I put a 2 out there in the front, which is going to stretch it to 2 on the y-axis. It's a vertical stretch of 2. If I put a 4, it's going to be a vertical stretch up to 4. If I put a 6, it's going to be a vertical stretch up to 6. So let me show you that visually. So here's my original. Y equals, there's an invisible 1. That's why it crosses at 1. But if I put a 2, it'll stretch it to 2. If I put a 4, it'll stretch it to 4. If I put a 6, it'll stretch it to 6. Make sense? So that number out in the front on this green one, it says y equals 6, and then you have the parenthesis base 2 to the x, right? That's this green one right here. It got stretched all the way to 6. It got stretched to 6 because the number out here in the front is a 6. What if I would have an 8? What would it be stretched to? It'd be stretched to 8. Are you with me? Okay. What if this was not an actual number? What if it was a 1/2? What if it's a fraction, which is still a number? But what if it's a small number like 1/2? Then it's no longer a stretch. What do you think it is? It's a compression, right? I know you guys just went like that with your hands. That's making it shrink, right? So if this value were a 1/2, as a matter of fact, I would like you to do that right now on Desmos. Type in 1/2 out here in the front of the parentheses with the 2 and with the x. Put a 1/2 right there, and you're going to see this guy get crushed down to the 1/2 spot. You're going to see a vertical compression. Go ahead and do it. Okay, so I just did that right here. There's my original, y equals 2 to the x, and then I put in a 1/2 right in front, and you will see that the original red one that originally crossed that 1 now got compressed, got smashed to the 1/2. So that number out in the front, Destiny, will tell you if it gets vertically stretched or compressed. If the value out in the front is a number bigger than 1, then it's going to be a stretch. If it were an 8, it's going to get stretched all the way to 8. But it's a 1/2, so it gets smashed down to 1/2. Okay? So the vocab words that we use a lot in Algebra 2, which you guys are going to need to know in the future, is vertical stretches and vertical compressions. Okay? So if the A value, the number out here in the front, is bigger than 1, it'll be a stretch. If the A value is a fraction between 0 and 1, if it's less than 1, it's going to be a compression. Let's move on. What if you compared your original y equals 2 to the x with a -1 instead of a 3 or a 6 or an 8? What if it's just a negative sign out here in the front? Go ahead and type that in. I'm going to pause it. And the question is, what happened to the graph by putting a negative sign in front of it? Or putting a -1 in that front value? Okay, so you guys just said that it goes opposite. It technically causes a reflection over the x-axis. So check out all these ones that I did that we're going to compare right now on the screen. We already know what the original one looks like. The negative will cause it to reflect over the x-axis. So if the original one, here's the xy plane, a quick sketch. If the original one was over here and then it grows exponentially, this one right here is going to reflect over the x-axis. It kind of got reflected over the x-axis. A perfect mirror image, but towards the bottom. Does that make sense? That negative sign caused the reflection over the x-axis? Now, what if we go to the -4? Well, the negative is going to cause this red one to reflect over the x-axis, but the 4 itself will cause it to stretch. So just a quick sketch, just so you could think about it. The negative sign is going to cause it to reflect, but then the actual value of 4 is going to cause it to stretch. So it's going to be stretched further. Okay. Obviously, we're going to type all of these. I already typed them all into Desmos. Okay, and let's compare. Here's your original, the red one. Y equals 2 to the x. But if you put a negative sign in front of it, it'll reflect this red one over the x-axis. Here's the x-axis. It's like if it were a mirror, if it were mirrored over to the other side of that x-axis. Okay, and this is y equals -2, close parentheses, to the power of x, and then this is -4, and then -6, right? So there's a couple of things to note, a couple of things to understand about that number that's out in the front. The number in the front of the base is known, outside the parentheses, is known as the A value. So everybody jot this down in your notes. This is very important. The number out here in the front is called your A value. Why did I put B right here? Because whatever number this is, that's what we call the base, right? And of course, it's an exponential function because you actually have a variable that's an exponent. Now, in addition to writing down y equals A times B to the x power, we want to talk about what this A value does. The A value tells you what? It tells you if it reflects over the x-axis. And how do you know if it reflects over the x-axis? If you have a negative sign as your A value. Okay? And it also tells you if it gets vertically stretched or compressed by analyzing what that number actually is. Okay? So if I took a look at y equals, let's say, 1/10, parentheses 2 to the x power, I know that the original graph, y equals 2 to the x, what happens to it? Does it get stretched or compressed? If your original one looked like that, then this new one gets compressed because of the 1/10. So it gets compressed, it gets smashed towards the x-axis. Make sense? Now, on the other hand, if you had a -1/10, well, it would still be that vertically compressed fraction, but it'd be reflected over the x-axis. Okay, now these are just sketches. We could all see them actually on Desmos. I think we demonstrated that already. But right now, it's important to know that this number out here in the front, it tells you if it reflects over the x-axis. How do you know if it opens down instead of up? If the A value is what? Negative, right? It's going down instead of up if it's negative. That's what you call a reflection over the x-axis. And it gets vertically stretched if your value is greater than 1. It gets vertically compressed if your value is less than 1. Okay? So 1/10, that's definitely less than 1. That's why it's compressed. Okay? Anyways, that's what the A value tells you. What if we added a constant value k at the end? Okay? So we already know what the A does. It reflects it over the x-axis. It gets vertically stretched or compressed. But what if I put a plus k at the very end? Okay, what I want you to do right now is go to Desmos, graph y equals, put a 1/2 out here in the A value. Put a 1/2 or a 1 divided by 2 out there in front of the parenthesis. Now you should already know that that causes what? A stretch or a compression? A compression. It smashes it closer towards the x-axis, right? But go ahead and graph that, and you'll see that it gets smashed a little. It's going to cross the y-axis at 1/2 instead of 1. Okay, and then in addition to that, do the same graph, but put a -3 at the very end. Okay, and you're going to see something happen. Go ahead and do that. Okay, guys. So I just asked what the k actually does when you, what this k actually does when you put a -3 right here. It brings the whole graph down 3. So let's start by looking at this one. Now on my graph, I typed in the original y equals 2 to the x, and then I typed in y equals 1/2, so you could see how it got vertically compressed by 1/2. Now if it would have been a 3 out here, it would have gotten vertically stretched, but it got compressed by 1/2. Okay, and then I simply added on a -3 at the very end. So let's compare these three functions. The first one is the original, the red one, y equals 2 to the x. And we know that that crosses right here at the coordinate 0, 1. Okay? And then we put a 1/2 in front. And what that caused is it caused this red graph to get smashed by a factor of 1/2. So where it used to be at 1, now it crosses at 1/2. So that would be right there, 0, 1/2. Okay? And then from there, because of the -3 that we added to it right here, the -3 as the k value, what it did was it took that original black graph, that black growth function, and it shifted it 3 units down. Okay? So let's say this nice coordinate right here at 2, 2, 2, 2, if I shift it 3 units down, 1 unit, 2 units, 3 units, I end up right here. Okay? And that makes total sense because that k value causes all the coordinates to shift 3 units down. Does that make sense? Okay? Now, what if I were to have, what if I would have put in y equals 1/2 to the 2x with a +1? Then that black one wouldn't have moved 3 down, it would have moved 1 up. So it would have been up here going like that. It would have moved 1 up. So that k value causes an up and down shift. Does that make sense? Okay. So in summary, the a value, it tells you if it's opening up or opening down, depending if it gets reflected over the x-axis or not, depending if it's positive or negative. And then after that, it tells you if it gets vertically compressed or vertically stretched, depending on the a value. And those are some good notes to know. The a value tells you if it reflects over the x-axis, and it also tells you if it gets vertically stretched or compressed. Obviously, if this was a 1/10, it would get compressed. If it were a 3, it would get stretched. If it were a 5, it would get stretched. If it were a -5, then it would get reflected over the x-axis, then stretched by 5. And this is literally Algebra 2 stuff, guys. So I hope we're following along and keeping up with this. Now, what do we call this? We call this the base. But what does that base actually tell us? That base tells us the growth or the decay factor. So the base, this guy right here, tells us if it's a growth function or a decay function. Now, we haven't even talked about decay functions yet. We're going to talk about decay functions tomorrow, okay? But it's the same concept if it's a vertical stretch or vertical compression. If this b value is a fraction less than 1, then it's going to be a decay function. If the b value, if it's a growth factor greater than 1, then it's a growth function, okay? So it says this b value is the growth or the decay factor. Up until now, you're only going to see like a 2 right here, or a 3 right here, or a 4 right here. Those are all growth values, so they will be growth functions. From left to right, they will grow away from the asymptote. So it tells you from left to right if it grows away from the asymptote or if it infinitely approaches the asymptote. Tomorrow, we're going to be dealing with fractions between 0 and 1, like 1/2, and that would be a decay function. That means that from left to right, it'll start way up here, and it'll decay towards the asymptote. But right now, it's just growth functions, values that are greater than 1, and they all grow from left to right, away from the asymptote. And what about this k value, this plus 3 or this minus 3? What that does, it tells you, whatever that k value is, it tells you whether your original graph shifts up or down according to that numeric value. Not only that, it also tells you the asymptote. What is the asymptote? It's that dotted line, that horizontal dotted line that your graph will infinitely approach but never actually touch. And the equation of any horizontal line is y equals a number, and specifically, it'll be y equals that number k. So this k value is super important. It tells you if it shifts up or down, and it also tells you that asymptote equation y equals whatever that number k is. Now, we haven't talked about h because h is the shift left or right. The k is the shift up or down. The h is the shift left or right. And that gets kind of confusing, and that's why we're going to hold off on h's until Algebra 2. In Algebra 1, we don't even put a minus 3 up here or a plus 2. We don't put anything. We only put an x on Algebra 1. But in the future, in Algebra 2, we will have an h value here, and that will cause a shift left or right. But right now, we're only going to worry about the k shift, which shifts up or down. And it also gives you your asymptote y equals that k value. So, with that said, I think you guys could graph anything on Desmos, and you should be able to see how the different a values affect it, how the different k values affect it, right? How a negative sign in the a affects it, right? But what if we asked you to graph without Desmos, or without your Chromebook, or without a graphing calculator? How do you graph an exponential function with an XY table, with a pencil and paper? Well, here are the steps. Step 1, identify h and k. Remember, Algebra 1, we don't even have an h. But in Algebra 2, you're going to have to identify h and k. Today, you're only going to have k values. And in this year, Algebra 1, you're only going to have k values. But you're going to identify h and k, and then you're going to ignore them. And then you're going to set up an XY table. This is an XY table. And you're going to use consecutive integer inputs. -3, -2, -1, 0, 1, 2, 3. Numbers that are in order on your x side. -3, -2, -1, 0, 1, 2, 3. And then the next step is to graph the coordinates of your function without the h or the k. How the heck do you do that? You plug in one easy number like 0. You plug in an easy number like 0. Plug in 0 into the x, do the math, and you'll get a number out here, and that'll be your first output. That'll be your first coordinate. And then, instead of plugging in more inputs, what you could do is use that output and modify it according to your growth value of b. So whatever this number is, and whatever that number is, you multiply it by that b value, multiply it by that b value, multiply it by that b value, and you'll have your other outputs, and you have a bunch of coordinates. We'll actually do this in a little bit. Right now, I just want to describe the steps. And once you have these coordinates, you graph them, but you got to shift your coordinates according to h and k. In Algebra 2. In Algebra 1, we're only going to be shifting up or down because we're not going to have any h values in Algebra 1. But when you get to Algebra 2, you're going to shift both h and k, left and right, up and down. Okay? That sounds confusing, but once you get into it, you'll see that it's not that bad. So let's go to this page of notes that we had yesterday, and let's jump right in to this most interesting one right here. I'm going to explain this one again anyway, according to these notes that we have right here. Step 1, identify h and k, then ignore them. Okay, so what is h and what is k? Well, h is the number that's being added or subtracted up here, right? Is there a number being added or subtracted with the x? No, huh? So the h value, h is 0. And what about the k value? What's the k value? The k value is -3. Excellent. Okay? So step 1, it said, identify h and k, and then ignore them. Step 2, set up the XY table. Which XY table? This guy right here. And use consecutive integer inputs like -3, -2, -1, 0, 1, 2, 3. Let's do that. So we're going to go over here to the side. We're going to do an XY table. -3, -2, -1, 0, 1, 2, 3. Okay? And then it says plug in one easy input and find the output. But then again, it says ignore your H and K. Identify H and K and then ignore them. And then you plug in one easy number like 0. So check it out. We're going to plug in the easy number like 0. And again, we are ignoring the K value of -3. We are pretending it's not there. Okay? So if I pretend it's not there, when I plug in 0, what's 2 to the 0? 1. And what is 1 times half? 1/2. So everybody gets a 1/2. When you plug in a 0, you get out a 1/2. Okay? Now, instead of plugging in 1 and all these other things, I want to look at my base value. This is a 2, which is the growth factor of 2, which means I could take this answer and make it grow by multiplying by that base, the growth factor of 2. So 1/2 times 2 will get us what? 1/2 times 2 is 1. And then 1 times 2 will get us what? 2. And then 2 times 2 will get us what? 4. And I could even go further, right? Put a 4 right here. And then 4 times 2 will get us what? 8. Okay, now backwards, if I'm multiplying by 2 going down, going backwards, it'd be dividing by 2 or multiplying by half. 8 times half is 4. Half of that's 2. Half of that's 1. 1 times half is half. What's 1/2 times 1/2? 1/4. And then 1/4 times 1/2, 1/8. And then 1/8 times 1/2, 1/16. And we get the idea that it's getting smaller and smaller and smaller going this way. So we could actually plot these points. Now keep in mind that these points are not the points to the entire graph because I've been ignoring the -3. These are the points to the graph y equals a times b to the x. So if I plot these points, let's start with 0, 1/2. 0 and then only halfway up. That will be right there. If I go to 1, 1, that'll be right there. If I go to 2, 2, 2, 2, that'll be right there. If I go to 3, 4, 3, 4 is right there. If I go to 4, 8, 1, 2, 3, 4, 8 would be up here. And we know that as we go to the left, it gets smaller and smaller and smaller until it looks like it's actually on the asymptote of y equals 0 because we ignored the k value. But we know that the k value is actually -3. So that means I need to shift all of these coordinates down 3 units. Because you guys saw in Desmos that the -3 as the k value causes a shift down 3 units. So you could begin with the asymptote value itself, or the asymptote equation. The asymptote equation is y equals k. In this case, y equals the k value -3. So the k value y equals -3. The line y equals -3 is 1, 2, 3. It's down here. I'm going to do a dotted line. This is my asymptote line. And this blue graph that grows needs to all get shifted 3 units down. So this guy gets shifted 1, 2, 3, and you end up right here. This guy gets shifted 1, 2, 3 down right here. Whoops. And then this guy gets shifted 3 down. Wait. This guy gets shifted 3 down. 1, 2, 3 right here. And gets shifted 3 down and 3 down and so on until you have your new graph down here. And from left to right, it grows to infinity. Do you get it? I hope so. Okay, now the domain are your x values of your graph. And the x values, well, your x-axis runs from left to right. So does the graph go to the left forever? Yes, it does. Does it go to the right forever? Yes, it does. Even though it curves up, it'll continue to exist right here, but just going to be way up there somewhere. It exists over here, just way up there somewhere. So it does exist to the left forever, to the right forever. So your domain is x equals all real numbers. You could technically plug in any x value you want into this XY table. You could plug in a -1000, you could plug in 400, you could plug in whatever number you want. So the x's, the x's could be any number you want. So the domain is x equals all real numbers. X equals all real numbers. What about the range? The range are your Y values, the up and the down. Okay? So the range values, does it go up forever? Yes, it does. This grows to the top forever. It'll reach to 10, it'll reach to 1,000, it'll go up forever. But does it exist at the Y value of negative 10? The answer is no. The red graph never reaches negative 10. It actually infinitely approaches that Y value of what? The asymptote Y value negative 3. So this whole red graph is above what value? Negative 3. So how do you say mathematically that your Y values are above negative 3 for your range? Your Y values are greater than negative 3. So that's your range right there. So the domain is X equals all real numbers. The range is Y is greater than 3. Y is greater than your asymptote value. Y is greater than your K value. Now the Y-intercept, that's just saying where would it cross the Y-axis? Well, it would cross the Y-axis right here at that location, which is the coordinate negative 1, negative 2, negative 2.5. So that would be the coordinate 0, comma, negative 2.5. That's the Y-intercept. So this is how to graph it without Desmos, right? So that original blue one, I would put like some X's on it so we don't get confused. That blue one's not the graph that you want. The final graph is the one that got shifted 3 units down according to that K value. So let's flip this paper over. We have some homework. We have 6 questions. Let's graph one of them. Which one would you like to see? The first one? Yes, please. All right, let's do the first one. Okay, now, first of all, I would put parentheses around the 3. That way we don't get confused. Or maybe even rewrite it. Y equals, your A value is technically a negative 1, parenthesis 3 to the X power, right? So I need to identify H and K. Is there an H? Nope. Is there a K value? No. So they're both zeros. That means we're not going to shift anywhere. That means that we identified them, we ignore them, but there's nothing to ignore because they're not even there. That means that this XY table will actually be coordinates of our final graph. We're not going to have to shift anywhere because we don't have an H or a K. We never have H's in Algebra 1. But we're not going to have to shift up or down. Let's use consecutive integer inputs, negative 3, negative 2, negative 1, 0, 1, 2, 3. You go to 4, however far you want. Anyways, let's plug in the easiest one, 0. When I plug in 0 into here, what's 3 to the 0? What's anything to the 0 power? 1. Okay, so we get out of 1. And then, but 1 times that A value of negative 1, what do I get? Negative 1. So everybody put a negative 1 for the output given the input 0. Now, I could plug in more values, or I could simply use the base, which is the growth factor, to make this answer grow to the next answer. So I'm going to take the growth factor of 3, and I'm going to take this negative 1 and multiply by that growth factor of 3. Negative 1 times 3, what do I get? Negative 3. And then times 3, what do I get? Negative 9. And then times 3, what do I get? Negative 27. And that's obviously off the graph. It's not even, there's no point in multiplying by 3 again to get to the next coordinate. That's ridiculous. So if going this way, I'm multiplying by that growth factor of 3. Going backwards, I'm dividing by 3, which is really multiplying by 1/3. So negative 27 times 1/3 is negative 9, times 1/3 is negative 3, times 1/3 is negative 1, times 1/3 is what? Negative 1/3. And then what is 1/3 times negative 1/3? Negative 1/9. And then what is negative 1/9 times negative 1 or times 1/3? Negative 1 over 27, which we know is getting smaller and smaller and smaller. So let's graph 0, negative 1. That's a dot right there. Let's graph 1, negative 3, right there. Let's graph 2, negative 9, down here. And if we graph negative 1, negative 1/3, negative 1, and only 1/3 of the way down, that's not even halfway down, you'd be right there. And then negative 2, negative 1/9, that's even closer to the x-axis and closer and closer and closer. Here's our graph. What's our asymptote? Our asymptote is the asymptote is the equation y equals k, my bad, y equals k. And what is the k value? 0. So y equals 0 is the asymptote, which is this horizontal line, y equals 0, the x-axis. And yes, of course, our graph infinitely approaches that asymptote. You could draw it like if it's actually touching, even though you know it doesn't touch, it just infinitely approaches. And from left to right, it does grow away from the asymptote. It grows away from the asymptote. That's a growth in a negative direction. Now you might be thinking, wait a minute, how could it be growing if it's getting smaller, it's getting more negative? It's a growth. It's like in the real world, a growth in a negative direction would be you getting some credit cards and just running up the credit cards. You owe more money, and more money. So it's growing in a negative direction. It is growing away from the asymptote. So I would like you to work on the rest of these. Let's take a look at this guy right here, number 3. Let's work on that one together. Let's identify h and k. In algebra 1, we're never going to have an h value because there's never going to be something added or subtracted with the exponent x. But we do have a k value. What's the k value? 5. Thank you very much. K value is 5. Now that already gives us our asymptote. That's the horizontal line, y equals that k value of 5. We'll get to that later. But right now, since we already identified h and k, I can now ignore h and k and just focus in on this and make an input-output table for it. Use consecutive integer inputs, -3, -2, -1, 0, 1, 2, 3. And I am going to plug in the easiest number, 0, into the boxed-in function. I'm going to ignore the plus 5. Just put it right there. 2 to the 0 is what? 2 to the 0 is what? 1. And then 1 times -half. What's 1 times -half? -half. 1 times anything doesn't change it, right? 1 times -half is -half. Just like 1 times 7 is 7, or 1 times Johnny is Johnny, right? So 1 times anything is that same value. Now, I am going to use the growth factor of 2 to get from here to the next output. So the growth factor of 2, what is -1/2 times 2? -1. And then -1 times 2, -2. And then -2 times 2, -4. You guys get it? So if you are multiplying by 2 as you go down backwards, you're going to be multiplying by the reciprocal of 2, which is really multiplying by 1/2. So -4 times half is -2. Half of -2 is -1. -1 times half is -1/2. What is -1/2 times 1/2? -1/4. And then -4 times half, -1/8. And then -1/8 times half, -1/16. And we know that's getting smaller and smaller and smaller in the negative direction on the x's. So when we graph 0, -half, we end up right here. When we graph 1, let me do this in blue though. When we graph 1, -1, we end up right here. When we end up graphing 2, -2, 2, -2 right here. 3, -4, 1, 2, 3, -1, 2, 3, 4 right there. And as we go -1, -1/4, you go -1, -1/4, that's half of the half. So it's even closer to the x-axis, closer to the asymptote y equals 0, closer, closer, closer. There's my graph, but that's only this boxed-in blue function, ignoring the 5. So what do I need to do to all these coordinates to include the 5? I need to add 5 to all the y values. In other words, shift all these coordinates 5 units up. So if I did shift this guy 1, 2, 3, 4, 5, I'd end up right here. And then if I shift this guy 1, 2, 3, 4, 5, I end up right there. And then I get this guy 5 up, it'll be right there. And if we thought about the original asymptote y equals 0, and now look at this new asymptote y equals 5, you might as well go to 5, 1, 2, 3, 4, 5, and draw your horizontal asymptote right through that y value of 5. So this is the asymptote right here. And as you go from right to left, it gets closer and closer and closer to that asymptote. So there's your final graph right there. I hope this makes sense. Please work through the rest of these. Check Google Classroom for the solutions, and we'll continue tomorrow.